Okay, we're going to work problem 2.125. This is an interesting problem. It's a couple collars that are sliding on some rods. And the interesting part of this problem is that we really only need to balance the forces along the slide, okay? We're going to assume that the transverse force that's perpendicular to the rod, not along the slide, will be whatever it needs to be to balance. I mean, it's constrained so it can't move, it can't move other than by sliding. And that's really the tricky part of the problem. So we have two forces. Force P, which is 341J, and we can see that here. Let's highlight these things just because. And we'll do that. We'll pick the highlighter here. And so we've got our force P here. Okay. And we need to counter that with the tension in the wire and our force Q, which we also need to counter with the force in the wire. Now we're going to draw the vector that describes the direction of the wire, the line of action. We're going to write that from A to B, and let's go ahead and label these a little more carefully. This, as the picture shows, is A, and this is B. Okay, let's draw the vector from A to B. We have to write out the position of A, and so A is 0, y, 0. That's right here. And just take that out of there, and B is down here at 0.20z. Okay, so notice the y here and the z here show up, and they show up in these expressions here and here. Okay, so the forces that we are applying are P, which is known, 341J, and force Q is Q in the K direction, and that's down here. Okay, so we need to define this lambda vector, and lambda vector goes from A to B. Let's pick a color here. Let's do blue. So it's really down doing that. That's the lambda A, B. Okay. So it's 0.2 minus 0, right? Endpoint minus starting point. 0.2 minus 0, and then 0 minus y, and then z minus 0. So we've got these components here, here, and here, which simplifies to that. So the magnitude is this, right? Just the square root of the sum of the squares. And so the unit vector will be very nicely, let's pick our highlighter again, is that over that, which is this nice expression. Now, we're given that y is a value, 0.155 meters, and we're also told the length of the wire is 0.525 meters. So I can use the fact that the square root of the sum of the squares gives us the length of that wire, and I put in the y here, and we could solve for z, so z comes out to be that. So we now know x, the y and the z that we need. Okay, so let's go to the next page. Okay, so I'm going to fill in the lambda AB, and I just filled in all the numbers, and then when I did that, I got this expression. Okay, so now I'm going to write the forces out again. So the P force we wrote, that's on A, and the Q force is on B. And then we're going to write the force on A is T times lambda AB, and the force on B is minus that, right? Because, and let's be a little more careful about our notation here, just to be careful. right? Should really do that and that, okay? Because the force along that wire, it's pulling on A and pulling on B, right? Cables pull, so we have to change the directionality. Okay, so the constraint is really that this RAY is 0 and the RBZ is 0. So the Y force on A is 0 and the Z force on B is 0. So we can actually write that out. Let's get our little highlighter back again. Okay, so the force on A is this 341, and then the force is in this J direction is just the magnitude times this component, which we got, from right here. Okay, and then on the Z, it's QK, that's our QK, and then notice we've introduced a minus sign here, right here. So now we have our constraints. We can solve this first equation for T, and T looks like this, right? We solved this equation for T. And now we can go on and solve the second equation for Q using our T. Notice that extra minus sign there. And so we get Q is that. Okay, so we've got all our forces. And the real issue in this problem is knowing that the only forces we have to balance are the ones that are moving along the sliding direction.